This is a supplement for General Physics 1. This is talking about circular motion, and in particular we'll be looking at acceleration in circular motion and the three different kinds of acceleration that actually come up in circular motion. So when you deal with motion in a circle, a couple good resources are to go to the PhET site, and I suggest you just search for it yourself on whatever device you are on, and look for a couple of different PhETs, including ladybug motion and rotation, otherwise known as ladybug revolution. They're good ways of practicing circular motion dynamics and changing parameters and seeing what happens. So when we look at circular motion, in particular, we're starting with circular motion at constant speed. And this kind of picture is the picture that we want to get really familiar with. I'm going to talk about the variables that we've discussed in class and that we'll continue to see. The first variable we're looking at is angular displacement. So angular displacement theta is defined as s over r. Well, S is a new letter for us. S is another letter for distance, and it refers to arc length. So if there is a certain theta that's traced out as an object moves in a circle, the arc length is the length of the path that the object moves along. So theta is defined as S over R in radians, and when we connect this to our linear variable S, we see that S equals R times theta. Now that we know the angular displacement, we can look at angular velocity. And the angular velocity is called omega. The omega is defined as change in theta with time, or delta theta delta t. And if we go to an infinitesimal time step, this would become a derivative, or d theta dt. So omega is defined as d theta dt. And what that means is the rate of change of the angle that something is traveling in or is sweeping out. So as it goes in a circle, you're looking simply at the change in angle as it goes around. When we want to connect this to our linear variables, v, we know that velocity we've called v, and we want to connect omega to v. V equals r times omega. All right, now we get to our first kind of acceleration, and this is angular acceleration. Angular acceleration is referred to with alpha. This is a Greek symbol, alpha, and alpha is equal to change in omega with time, either delta omega delta t or just d omega dt as written here. So there is angular acceleration when the rate of change, when omega is changing. In other words, if something's speeding up and slowing down as it goes in a circle, there would be angular acceleration. We connect this to our linear variable, a sub t. The sub t here refers to tangential. So a sub t is the tangential acceleration as an object goes in a circle, and a sub t is equal to r times alpha. Notice a similarity with all of these linear variable expressions, that in each case you take the linear variable and that is equal to r times the angular variable. So r connects the linear and the angular variables. There is also a direct relationship between angular and linear variables when we look at constant acceleration. We started the semester with constant acceleration in one dimension and linearly, and now we're doing constant acceleration in a circle, or angular constant acceleration. The equations are the same. This is very useful to have written on your note card in any case because it's harder for us to just translate v from omega in our heads, so it's good to have it written down. Notice that in all of these, the acceleration is alpha, not a, but alpha over here on the left-hand side. Okay, so now we come to a second type, actually a third type. We've now talked about tangential acceleration, angular acceleration, and now we will talk about centripetal acceleration. So any object that is executing circular motion at any speed, but if it's executing circular motion at constant speed, it has an acceleration of constant magnitude directed toward the center of its circular path. So that means this object, as it goes in a circle, the velocity is tangential to the circle, the radius of the circle, or our r vector, is directed out towards the object, And the centripetal acceleration will be directed towards the center of the circular path. So we call this centripetal acceleration, and this is an acceleration that's needed in order to keep an object going at a speed v in a circle of radius r. It is not something that you add. Centripetal acceleration exists whenever an object is going in a circle. In other words, it must have centripetal acceleration to go in a circle. So we're going to do a quick derivation here. We can, using just this diagram, we're going to derive the expression for centripetal acceleration. So here we've got a triangle. We have an initial position, which is right here, v at vi, and then this object's going to go in a circle, and it will now, this is at ri, it will now be at rf, final position. We can see that the velocity changed from vi to vf, and the change in displacement was theta, in angular displacement was theta. Okay, so we're going to draw two triangles. One triangle is this triangle with the r's. R initial, R final, and delta R between R initial and R final. Another triangle is the V's, V initial, V final, and delta V between V initial and V final. We're going to relate those to find centripetal acceleration. So we know that centripetal acceleration is defined as change in velocity over time. And in this case, it's the V, the tangential velocity here, that we're talking about. So that's what we're looking for. Now let's write out what's going on with our triangles. This expression on the left, delta V over V, is looking at this little green triangle, delta V over V. In other words, the short side of the triangle divided by the long side of this isosceles triangle. Right here we've got delta R over R, and that's the short side of this triangle divided by the long side of this isosceles triangle. And these are similar triangles, so delta V over V equals delta R over R. We multiply both of those by 1 over delta t. And then we're going to do some algebra and simply rewrite delta V over V. So on the left-hand side, we have delta V over V. If we multiply by velocity V, then we'll have V times delta R over R times 1 over delta t. So delta V over delta t is equal to the centripetal acceleration, and this is now equal to V over R times delta R over delta t. But what is delta R over delta t? That is simply the definition of velocity. So this is V over R times V, which is just V squared over R. And there we go. Centripetal acceleration equals V squared over R, where V is the tangential velocity. So again, these two similar triangles are what has shown us that the centripetal acceleration is equal to v squared over r for an object moving in circular motion. This picture here helps us to again look at what the different variables are. The tangential axis is the one that's tangential to the circle. It points in the direction of increasing theta, as is written here. The radial axis is away from the axis of rotation, and the z-axis here is out of this plane, and the z-axis is, we would refer to that as perpendicular to the plane of motion. Okay, so with this definition, with that figure, we can see that the radial acceleration, a sub r, is equal to minus v squared over r. Now, why is that a minus? Simply because it's pointed, a sub r, the radial acceleration is pointed towards the center of the circle, but the positive direction for r is towards the outside of the circle. Look at this r vector here. So the radial acceleration is in the negative direction. It's towards the center of the circle, which is the negative direction. All right, so if we were looking for the total acceleration of an object, we now have lots of accelerations to deal with. One thing we can find is angular acceleration, d omega dt. And then we can also look for the linear accelerations. Here, this picture shows a point on a wheel. The wheel is rotating this way. And there's radial acceleration inwards, right? And that is equal to our centripetal acceleration. in magnitude. And there's also, let's say, tangential acceleration downwards, tangential to the circle. In other words, if it's speeding up or slowing down. So we have our tangential acceleration, which is equal to alpha times r, our centripetal acceleration, which is equal to v squared over r, and our linear acceleration then, our total linear acceleration is like this vector a, and that is equal to the square root of the centripetal acceleration squared plus the tangential acceleration squared. In other words, this is not a new equation, this is simply the Pythagorean theorem for a right triangle with radial acceleration and tangential acceleration. There's a little bit of back and forth between a sub c and a sub r. In the picture it's a sub r, here it's a sub c. If we're dealing with magnitudes, they are the same thing. Okay, so let's do an example of this. Okay, we're going to analyze how to answer this problem. So in this case, we have a wheel, as says in the description, that started from rest, and with a constant angular acceleration speeds up to a speed of 100 revolutions per minute. The time it takes to speed up to that rotational velocity is 8.0 seconds. Okay, so the first thing we'll do is calculate the cyclist's wheel's angular acceleration. So for part A, we will find the angular acceleration. And the angular acceleration here is alpha. Right? So that's identifying the variables is really important as we start working with different accelerations and with circular motion. So let's think about what our definition is of alpha. The angular acceleration alpha equals the change in omega with time, where omega is the angular velocity. So when we're looking for our, let's draw a picture and understand what's happening here so we can figure out omega and alpha. We have a wheel. Say the wheel is rotating this way. So our omega is in that direction. If we looked at a point out here on the wheel, there would be a velocity, tangential velocity, like this. The radius of the wheel, just draw the radius, put it here. The radius of the wheel is from the center of the circle to the rim of the wheel. And there is some acceleration. There is some tangential acceleration and also some angular acceleration. So in this problem, we're given information about how the angular velocity changes with time. Let's write this out again. Delta omega is omega final minus omega initial over the total time, delta t. And our omega initial in this problem is 0 radians per second. Our omega final is 100 revolutions per minute. And that is not the kinds of units we want to deal with. So we'll convert that to radians per second. So our revolutions per minute, let's multiply that. We want to end up with radians and seconds. So if we have minutes on the bottom there, let's put minutes on the top, seconds on the bottom. 1 minute is 60 seconds. And now we want radians instead of revolutions. So we'll put revolutions on the bottom, radians on the top. And a single revolution is 2 pi radians. So we have 2 pi radians per 1 revolution. When you multiply all of those values out, omega final is going to be 10.5 radians per second. All right, so we start at 0 radians per second, we finish at 10.5 radians per second, and that will tell us what the angular acceleration is. Then we come back, let me just write omega final here. We come back to our alpha. Our alpha is now 10.5 radians per second minus 0 radians per second divided by delta t, which is 8 0.0 seconds. And when we multiply and divide those numbers out, we should get 1.31 radians per second squared. And since we have only two significant figures in this number, we'll have to reduce that to just 1.3 radians per second squared. Okay, so that is the angular acceleration. I'm going to write it up here as our answer, 1.3 radians per second squared. Now we're going to move on to the next part of the question. So we'll erase this. And let's figure out what the total linear acceleration is. So part B. Find the linear acceleration. And this we will just call A. And so with our picture here, we have the wheel is speeding up. So we have some acceleration this way, which is the tangential acceleration. It's going in a circle, so there's also centripetal acceleration, acceleration towards the center of the circle, which we'll call A sub r. And the total acceleration is the addition of these two vectors, and this is our vector A. So this is a right triangle, which I can draw again down here. There's the vector A. And it has two sides, two components, A sub r and A sub t. A equals the square root of A sub r squared plus A sub t squared. Okay, so let's figure out how to substitute in some values and concepts over here. We're looking for our linear acceleration A, and we need to know the two different components, the radial acceleration and the tangential. Start with the tangential acceleration. Tangential acceleration, as you saw earlier, is equal to r times alpha. So we'll just leave it as that. Tangential acceleration is r times alpha. We know the radius is equal to 720 millimeters, which is 0.720 meters. And alpha is, as we found before, 1.3 radians per second squared. Okay, so we have all of the values for that. We don't need to plug it in right now. The radial acceleration is equal to v squared over r. And we found omega, not v. So instead of redoing more math, let's just do some algebra. Rather than v, we're going to substitute v equals omega times r squared divided by r. So v equals omega r. And that becomes omega squared times r. Okay, so our radial acceleration is now omega squared times r. This will give us our final acceleration, which is the square root of a, write it out that way, a r squared plus a t squared. And this is now equal to the square root of omega squared r squared plus r alpha squared. And we can plug in numbers for this. We find using omega, which we had on the previous 10.5 radians per second on the previous board, and r, which is 0.72 meters, and alpha, which is 1.3 radians per second squared. Put all that together, and we will find that a sub r equals, A equals 79 meters per second squared. Okay, so write all of those out, run out of space on the board, using units, and that will give you the total acceleration. And let's just bring it back to the picture again. What we just found was this acceleration A. The total acceleration, it's actually pointed sort of downwards, not directly towards the center of the rotation, but a combination of towards the center and straight down the board, which gives us a direction sort of downwards like that, with a magnitude equal to AR squared plus AT squared. Right, and that's how we solve that problem.